Okay, good morning everyone and welcome back. Here we are at the beginning of the course on environmental bioethics within the Master of Bioethics at St. Thomas University. And we have 7 modules ahead of us this semester, all right? Let us begin always with a little prayer in the name of the Father, the Son, and the Holy Spirit. Come, Holy Spirit, fill the hearts of your faithful and enkindle in us the fire of your divine love. Amen. Okay, everyone doing okay? Doing good? Brief question about the statistics course. Has that begun? Yes, and she's doing Zoom or recorded lectures? Yes. All right. So you can follow the recordings. And she told me she would be available if there's consultation, right? All right. So far, so good? All right, good. Excellent. Let's move forward then, unless there is any question or comment, as always, from previous lectures or anything at all in the program or out of the program. Okay, well, we are halfway because now we have this summer and then the second fall, and that's it. In fact, the fall semester, it's only the healthcare bioethics course. So I keep emphasizing the internship hours. More and more places are opening up, and therefore seek a place if you are not doing the hours yet. Seek a place for internship. If you need assistance in that, let me know. But a number of places are already opening up where you can do your internship. Otherwise, the forest here is still available, always giving 3 for 1. All right, so that's an incentive. All right, so now we're going to shift a little bit in that so far we have been looking at bioethical issues mostly in human life at the beginning and at the end of human life. We're going to pick up a little bit back where we began the program with the whole issue of phylogenetics, looking at the evolution of the human species. At that point, I had already made reference a little bit to the origins. We were looking at 3 origins from that perspective, if you recall: the origin of the universe, the origin of life on Earth, and then the origin of human life, right? So there's a certain sequence and logic to that. The one presupposes the other. In other words, to have human life, first we need to have organic life on Earth. And to have organic life, first we need to have an Earth. And the Earth, of course, is part of the universe. And that's why those 3 origins, to the point that we can tie the very beginning of the universe with the most prevalent theory today, still to this day, what is known as singularity or the Big Bang, popularly known as that explosion, something from nothing. In fact, everything from nothing. Getting a little bit ahead of myself here, but it's just that it's trying to tie in this course now on environmental bioethics. What we're going to do, we're going to expand from the human person out to the environment, because certainly we don't live in isolation. Rather, we live not only in human communities, but these human communities need to live physically somewhere on Earth. So we can talk about the footprint of the human population on planet Earth, and also a tie-in to all of the environmental issues that surround us, right? They are critical and urgent. Not a week goes by, like I say, without a new bioethical issue or the recurrence of a bioethical issue on the horizon. I forgot to send you, but I'm going to, if I remember after the lecture or maybe at the break, I'll send you an article that just came out this week on the BBC. I mean, literally not a week goes by without a bioethical issue on the horizon. This one is precisely on bioethics, on environmental bioethics. And the title is pretty drastic, is something like this: are we destined to destroy all life on Earth? Are we destined to destroy all life on Earth? In other words, this one species, looking at it from the biological perspective, one of the approximately 2 million species that have been classified so far, and the approximately 10 to 20 million species that are estimated to live on Earth, we are the only ones with the capacity, with the real certain capacity to destroy the whole Earth, to destroy life on Earth. All right, that is very well known already for decades, ever since the nuclear age, for example. But now the big thing, of course, is pollution and contamination, and also the very footprint of the human population on Earth with regards to biodiversity, right? Encroachment on nature, which we have to live somewhere, because again, we don't live in thin air. We have to live somewhere, and wherever we live, we establish a footprint. So we can see it even here at St. Thomas University, our little St. Thomas University, where we have 140 acres, and we have already developed about 120 of them. So we have that 20 acres of the forest that we try to preserve, but everything else is developed, basically the footprint, right? So when, what is the carrying capacity is one of the questions that we can ask for the human species, a big unknown. Anyway, getting again a little ahead of myself, but this course I hope you find relevant, exciting, and important, and critical, and challenging with the contemporary issues on environmental bioethics. All right. So, like I mentioned, we have 7 modules ahead of us, and we'll go by stages. We'll look first at the Earth as in itself. We'll look at the different components of the biosphere. The biosphere is life on Earth. That life, again, needs to exist physically on a substratum, which is the surface of the Earth, whether it's land or water. And so first we're going to talk about geosphere today, the geosphere. Then we'll look at the atmosphere, which is that thin layer above the geosphere that is also keeping us alive and keeping foreign objects from hitting us drastically and exterminating us. Just to give you a very, very brief example, you look at the moon and they say it looks like Swiss cheese, right? It's all perforated with craters. Imagine, we can see those craters from here. So they are huge and extensive, and that's because the moon has been pelleted with, bombarded literally with asteroids and meteorites over the eons, and the moon has been in orbit for as long as the Earth has been around, more or less, about 4 billion years. So we should look like the moon if it were not for the atmosphere. So the fact that we have life on Earth, a lot depends on that little thin layer of atmosphere that we have surrounding us, okay, which is an incredible shield. Just sheer Earth, air is a tremendous shield from all the flying objects at incredible speeds coming our way. All right, then the hydrosphere, obviously, the water component, whether it's fresh water or salt water, which is most of the surface of the Earth. Talk about 3/4 of the surface of the Earth is covered by water, and about 90% of the volume of the crust is covered by water, the oceans mostly. All right, that's the hydrosphere. Then cycles, that's when we're going to get a little bit more into nature itself and the cycles of the abiotic factors, how they affect the life on Earth. Energy, also we devote some time to energy. Then the human population as this one species that is on the surface of the Earth. And finally, the topic, the overall topic of climate change and all the derivatives of that climate change, also kind of slash, I should put there, climate change slash environmental pollution, all right? We'll get there toward the end. Okay, so again, if there are no questions or comments, I'm gonna move forward. Sorry, forgot to turn off the lights here. Okay, better. Here we go. So for this lecture, we have several points to cover, beginning with the big picture again, a review of the origin of the universe, then the origin of Earth itself, geophysics, plate tectonics and continental drift. Then we'll look at the life, the life component on Earth, biomes, and the relationships of various organisms and populations on Earth, food webs and food pyramids. And finally, we're going to look at the hierarchy of organisms from the population on up all the way up to the biosphere as a whole. All right, so populations at the most local level and at the biosphere at the most global level of living organisms on Earth. So moving forward, let's look at this origin of universe. First of all, the amount of matter and energy that we can actually measure in the universe is very small. It's estimated to be only about 5% of what I'm calling visible matter and energy, simply to contrast it to dark matter and energy. All right, and these are the approximate percentages. That visible matter and energy is about 5% of what is estimated to be the full component of the universe. I'm talking about the physical universe where we exist as this little tiny dot within the planet Earth, within our solar system, embedded within the galaxy of the Milky Way, which is one of the billions of galaxies that live and are existing in the universe. Think about this for a moment. I'm talking about the visible matter and energy. In other words, all of the solar systems, we know that a sun is another word for a star, basically. And it is mostly a gas that is ignited and is in a plasma state, is that fourth state of matter, right? It's neither solid nor liquid nor gas. It is gas, but it's ignited, so it's equivalent to a flame. It is in that state that we call plasma, unstable, and yet at the level of stars, it lasts billions of years, ignited. So you can imagine the amount of gas that is there. It's just incredibly exorbitant. That gas is ignited and burning, essentially, for billions and billions of years. Okay, so that would be matter and energy, the whole lot of matter and energy that we can quantify of the entire universe. You can think of galaxies, nebulae, certainly all the solar systems and planetary systems and so forth, asteroids, meteorites, everything that's flying out there, only comprises about 5%, an estimated 5% of the universe as a whole. Another quarter of the universe is what we call dark matter. And it's called dark because light does not exit. In other words, it's super high density. Here we need to also recall the four forces, the four fundamental forces of the universe so far that we have been able to discover, which are the strong force and the weak force, and then electromagnetism and gravity. The first two are at the super macroscopic level, at the atomic level, the strong force and the weak force, and they're also known as attractions, and it's essentially what's keeping the atom together as a stable unit, as a stable unit of matter. And the other two are on the opposite end of the scale, at the large scale, the macroscopic and super macroscopic world. If you remember that, that little scheme that I had proposed, right? The microscopic, the macroscopic, and the super macroscopic. So electromagnetism and gravity, which are also known as fields, just for mentioning, electromagnetism is essentially if we run electricity through a wire, for example, or a conductor, that electricity, which is flowing in one direction, right, will generate a magnetic field around it, which is perpendicular to the motion of the electrons, all right? and that's a magnetic field. You can think of the magnets that we used to play with when we were kids, and we put iron filings on the paper, and we see that field defined by these semicircles, right? You have to consider that that's actually a dome. So if the filings could float, they would go all around on top of the paper and below the paper also, all right, to form a sphere around the magnet, or several spheres, concentric spheres. Similar, we have gravity. And gravity is an attraction force. So that's the one I want to concentrate a little bit on, gravity. It's in the background of what today's lecture, at least the first half of the lecture. Consider the phenomenon of black holes, right? Black holes are a big component of this dark matter. Those holes, what's at the center of a black hole is so dense, the matter that is so dense there that not even light is able to come out. Okay, so the gravitational pull has to be stronger than the speed of light, which is 300,000 kilometers per second square. Sorry, 300,000 kilometers per second. It's speed, all right? And that speed of light, well, gravity is at the center of these black holes is so strong that is stronger than that speed. Doesn't allow light to come out. Photons are trapped. And so anything that comes near a black hole will get sucked in. And you can see that as matter and energy get sucked into a black hole, it is feeding itself and becoming even stronger and stronger and stronger and stronger because it becomes even more dense, right? So black holes are all over the place now. They've been discovered out in the universe. And one theory says that one possible death of the universe is that it gets sucked into all of these black holes. And through there, no one knows what's going to happen afterwards. There could be like a second explosion. Maybe black holes will start cannibalizing each other and making these mega black holes, right? When one black hole comes close to another black hole within its gravitational pull, it's conceivable that they get sucked in. And maybe, so that may be one possible end of the universe eventually going. And then what will happen once those, let's say hypothetical, all of the black holes get eventually absorbed into one mega gigantic gargantuan black hole, maybe that thing then explodes at some point, and we would have like the birth of a new universe. And that's when some people talk about pulsating universes, and we are in the midst of one of those pulses. It's conceivable because the evidence is pointing to the expansion of our current universe, the expansion and the acceleration, not just speed, but actually acceleration. Very strange phenomenon. We'll look at it in the next slide a little more detail, but all this to say that basically this matter that we cannot measure directly, but indirectly, is about 27% or about a quarter of the matter of the universe, right? Of the stuff of the universe, for lack of a better word. How do we know black holes? Well, because when we look at the universe, when we look at stars and constellations, I've told you already that when we look up in the sky at night, we see basically globally two types of stars. We call them stars in quotations. The little dots and the big dots, the little lights and the big lights, right? Proportionally speaking, we can cluster them in those two groups. And neither one is actually a star. That's why I'm putting star in quotation, because the big ones are actually planets in our solar system, in our planetary system mostly, and they are reflecting the light. So they're opaque bodies. They're not luminous bodies like the sun. For example, Earth is an opaque body. We don't generate our own light. We generate heat, but not light. And so with the other 8 planets of our system, the other 7 planets, okay? We have 8 planets, I'll get to them in a minute, in our solar system. So when light hits Saturn and that light, the sunlight reflects to us, then we see this bright light up in the sky, and we think, oh, a bright star, but it's actually Saturn or Jupiter or one of the, typically the large planets. It could be also Mars or Venus. That also means that if we were standing on Mars, we would see the Earth as a star, right? Because of the reflection of the sunlight hitting us and reflecting onto Mars. Okay, and then the little dots, the little tiny ones, are actually galaxies, which are trillions of suns, and we can assume, in fact, a number of them have been discovered, actually planetary systems, those are called the exoplanets, right? Planets that exist outside of our own planetary system, which are out there, and they, we can hypothesize that they are in, conceivably in the trillions, these exoplanets. So the possibility of life out there, well, it comes to basically if they can have liquid water, because at least life as we know it depends on liquid water, right? And it's conceivable that at least one of these trillions of exoplanets may have conditions very similar to Earth. Why not? We're here, etc. Anyway, what I'm trying to say by all this, what is it that I'm trying to say? Yes, that, oh yes, so going back to the evidence for black holes, is that we see the starry night, right? And on a very dark night, in other words, without a moon, and especially when we're outside of the atmosphere to get rid of the reflection of the atmosphere, the noise, the filtering that the atmosphere causes, we have, you know, now observatory telescopes that are astronomical telescopes. They're satellites, right? So they're outside the atmosphere. They get much clearer, much deeper photographs, more stable, because there's not that filter, that noise of the atmosphere. Where we should be able to see galaxies, we see a blank, we see literally dark. And so those dark spots that appear on the sky where there should be galaxies, all right, in the background, those are black holes that are in between the galaxy and us. And that's how they have been spotted. Okay, but it's indirect. We can't measure them directly because we cannot get inside, literally inside dark hole. I think there have been some estimations of the gravity and the density of this matter. Okay, but they're estimates, and these are all mathematical models. Now, dark energy is a different story. It's a different type of darkness, all right? Dark energy, I was listening to a philosopher of science who was doing a biography on Einstein, actually. Has a series of tapes of recordings in this outfit called The Teaching Company, all right? Their videos, their CDs. And he says, we call it dark energy because we're basically in the dark as to what it is. But it's not matter. It's not black holes, for example, all right? It's energy. And it's about 3/4 of the universe, okay? It's about 70% of the entire universe is this dark energy that is estimated through mathematical calculations, and I think some of it has to do with what is known as the background radiation that I'm going to talk about in a minute, but basically it's estimated at about 70% of the universe is actually this energy that we can't really measure, that it's out there, and it's not the familiar energy that we are familiar with, like, for example, electromagnetism or gravity or heat or light, etc. Okay, these are different types of energy. No, none of that. So this, if nothing else, should make us very, very humble that we are this little tiny microscopic dot inside this 5% of the entire universe. Okay. All right, let's have a little visual here of what is a model of the universe with its two big stages. The two big stages, well, of course, after the Big Bang, we have two stages. one that is known as inflation and the other one known as expansion. All right, so inflation and expansion. And again, within the time space, the model of time space, because time and space are inexorably tied in together. All right. For example, locally, we can say that we are here in the same space that we were a few minutes ago and from the time I began the lecture. So time has passed and we are still in the same space. However, with regards to the rotation of the Earth, we are no longer in the same space that we were half an hour ago. All right, if we put a dot, hypothetical dot of where St. Thomas University was on planet Earth half an hour ago, that spot has rotated since, right? And so we're no longer at the same space in relation to the planetary system, for example, not to mention the galaxy and other galaxies, etc. So really time and space, even though locally that space seems to be still and static, in relation to the planetary system, for example, even just the rotation of the Earth, it is dynamic, all right? It's dynamic and it moves with time. So we talk about the time-space continuum or the time-space dimension together. All right, so these two moments, right, or phases, the inflation takes place within fractions of 1 second, down into 10 to the minus 10, 10 to the minus 20, I think almost 10 to the minus 30 seconds. So microseconds is the inflation, the very beginning. And after that, the scale changes all the way to the other end of time, all right? Very quickly through seconds and minutes and hours and years, it goes into the millions and very quickly into billions of years. And now the expansion phase, the second phase of the universe, the expansion phase in time slash space is now measured into billions of years, estimated close to 14 billion years so far, 13.7 billion years, okay, that we are away from the Big Bang, both in time and in space. And so we see almost the two ends happening, first with the inflation within microseconds, within 1 second, within the micro of 1 second, and then the scale changes quickly to the opposite end into literally billions of years in the expansion model. And it is, the rate changes quickly. Why? Because it is an acceleration. Keep in mind the distinction and the difference between speed and acceleration, right? So they are velocities, but one is a constant velocity. If I'm on I-95 at 65 miles an hour, and I set the autopilot on the car, right? Then the car maintains that constant speed at 95, at 65 miles an hour, whatever it is. That's constant speed. But acceleration is speed square, right? It's speed square. So it's a constant acceleration. And we can have constant acceleration, or we can have accelerated acceleration also, where it can be square, cube, and we can increase also the exponent of the acceleration. So either way, we can have a constant acceleration, for example, speed square, but we can also increase the exponent geometrically or even linearly, right? And that is going to cause an accelerated acceleration. And that's what's happening to the universe. Very strange, very interesting that the thing is expanding and expanding faster and faster. And that's why it's represented as this cone, not even a cylinder, but it's opening to who knows when and where. And they're placing in this model anyway, they're placing dark energy, you see, with a big question mark outside. Because all of this, right, in the diagram here, all of this is only 5%. all of what's included, all the stuff in here, all of the galaxies and the energy that's included, it's only 5%. All right. Well, no, I take it back. The black holes would be in here because it is matter. So the black holes were in here. So this is actually about 30%. 30%. The other 70%, who knows? We know of it simply because of what is known as the background radiation. This stuff that has been left behind from the origin of the universe from the time of the Big Bang. Okay, it's called background radiation or cosmic microwave background, to be more precise. And this stuff that is hanging around there in the background is like a backdrop, all right, to the universe, which has been already detected. For example, Hubble telescope, which is outside of the atmosphere, has been able to see back into the background radiation. And that's also how we know that we are approximately 14 billion years out from the Big Bang. Okay. All right. Anyway, let me move forward because this really is a realm of astrophysics, of which I have less than zero competence. But I do want to point out how the elements came about. They come about mostly in the inflationary model of that process. You see here, 10 to the minus 43 seconds, all right? It is so small in time and space because everything just before that, let's say if we go 10 to the minus 44 second, we're at the moment of singularity. Okay, ex nihilo, from nothing, something, in fact, from nothing, everything. And that's why, in fact, the fellow who proposes this model is Georges Lemaitre, who was a priest, who was a Jesuit priest. Interesting that the model for the origin of the universe is a priest, a Jesuit priest, who was also an astrophysicist. And also the father of genetics is also a priest, Gregor Mendel, who was an Augustinian monk in Brno, about close to 200 years ago, about 150 years ago, more or less. At the time of Darwin, I talked about that in the first lecture, about him. Anyway, so here is the inflationary model of the origin of the universe. The subatomic elements, all right? So the stable unit is the atom, but the atom only comes around here. Hydrogen would be considered the first atom around 1 second, which is a long time after the Big Bang when we get into the microseconds, okay? Into the microseconds. And before the atom, we need the subatomic particles, which are protons and electrons. But now we know that they are also composed of subatomic particles, which are basically the quarks. And now there are some physicists, the quantum mechanics physicists who are talking about subatomic particles of the quarks. They're calling it quantum foam. My brother was telling me about this the other day, quantum foam, for lack of another name. It gets stranger as we go deeper in, but apparently the quarks also have been found to have some components to them. So then therefore they are not the most elemental particle that we know of. At any rate, within 1 second already we have the hydrogen, which then with further coalition can become helium. And as we continue to add protons to the nucleus, right, we go through the table of elements, lithium, boron, etc., to build up the elements of the universe. Little by little, as coalitions occur with mostly protons and getting attracted into what is the strong force, which is what keeps the protons together, the strong force, and then the neutrons, which also add on to the mass of the atom, as we know, at the nucleus, which are held together by the weak force and the decay of neutrons into different isotopes, etc., within the same element. Anyway, little by little, we have the formation of the table of elements, which continue to coalesce and form more and more matter. But now we shift into the scale of billion years. And gravity is the one that more and more takes over as that fundamental force of attraction and making stuff coalesce and collapse into greater and greater matter, because matter exerts gravity. All matter exerts gravity. And so we come into the accretion model, all right? The accretion model of the planetary system. As cooling goes on, gradual cooling, in other words, heat dissipates. As you know, there's entropy, right? The buildup of entropy. Heat dissipates out, and there's a cooling effect on that matter, on the energy, on the matter first. Those gaseous nebulae begin to collapse, and they form these disks that are called accretion disks. Remember that accretion is just a coming together, a collapsing into itself of more and more matter. But there's also a spinning effect. These disks are also rotating at tremendous speeds. So some of that matter is coalescing around the periphery of the core, and the core becomes a star or a sun, properly speaking. And then the peripheral matter that gets trapped into the gravity of that sun, imagine how much matter, gas has to be there to exert gravitational pull on the planets. That accretion phenomenon continues to occur of the collapse of matter into itself, forming eventually planetary systems, the individual planets, and that is known as the planetesimal hypothesis, okay, the planetesimal hypothesis. And it's a gradual cooling effect. That cooling then allows matter to exert more and more gravity and attract more matter that is flowing around nearby, making it more dense until eventually, let's say that it runs out of matter that is in the immediate surrounding by its gravitational pull, because that gravitational pull dissipates also with distance from the center, right? And so they become more or less stable into what we call planetary systems, which typically has a sun at the center with planets around it. And the sun, like I say, is in a plasma state, and therefore is luminous because it radiates out not only heat, but also light, photons, whereas the planets themselves are opaque because they don't radiate light, but they do radiate heat. They absorb light, and in that energy transformation, heat is lost. Plus, the heat from the inside, from the core and mantle of these planets also, the heat is dissipating out into the universe, all right? So increasing that entropy or energy that is unavailable for work. Heat, essentially, that dissipates throughout the universe. All right, so let's look at our planetary system very briefly. We have three types of planets. We have the inner planets, we have the outer planets, and we have the dwarf planets. And more or less, it's by size, but it happens to be also by place, so that the inner planets are smaller, and they are in sequence away from the sun: Mercury, Venus, Earth, and Mars. So we are between Venus and Mars, right? And that is just the right distance for having liquid water on Earth. So that if we are at Venus, basically the water is, the Venus is too close to the sun and water will be in vapor state. Whereas if we are in Mars, then Mars is already too far from the heat of the sun, and therefore the water is frozen, at least currently, in their current orbits. But Earth happens to be at that just the right distance to maintain liquid water on Earth, which is a very narrow margin of temperature. We'll get to that in a minute in a little closer detail. But to continue the argument of the planets, then we have the outer planets, which tend to be large, as you can see, beginning with Jupiter, Saturn, Uranus, and Neptune. Used to be Pluto, but Pluto has been demoted to a dwarf planet because of its size. Also because it has an awkward, weird orbit, really, and that's why it's not shown here with a line like the others. First of all, these orbits typically are not circular, but elliptical, which means that sometimes they're close to the sun and sometimes they're further away from the sun. But Pluto has a different orbit, even a different angle and so forth. So it's estimated that it is an exoplanet that got stuck in, got trapped into the gravitational pull of the sun, but stabilized just like our moon by entering at a particular angle whereby the centrifugal force and the centripetal forces balance each other out and maintain then an orbital system that is more or less stable for now, hasn't not collapsed into the sun or flown out yet, all right? Then we also have other smaller planets that are called dwarf planets, like Makemake out there and Haumea, then Eris on the outer end of things. And on the inner end of our solar system is another one here, Ceres, okay? And these also tend to be near belts of asteroids. There's an inner belt that is in between the inner planets and the outer planets. And then there's an outer belt that is pretty much on the outside periphery of our planetary system as a whole. So it's a nice kind of composite system there. But of course, the dynamics of these orbits are quite interesting and complicated, being elliptical orbits and so forth. So we can talk about alignments and all that. Fine. Keep in mind that all of these planets are also exerting gravity and gravity upon each other and so forth. Also, when there are moons, and Saturn is the most drastic one because this disk is actually moons and it has its own belt of asteroids and stuff that is flying around it, okay? We have one moon and it also got stuck into our planetary system, into our gravitational system, so that the two forces, it's vectors, right? The centrifugal force is the force by which the asteroid is coming in to close to the planet, but would tend to continue in a linear trajectory, a straight line. But then centripetal is the gravitational pull on that object as it nears the Earth or any other planet, right? Pulling it in. And when those two forces kind of balance out, the resulting vector is going to be a spin, a translation, a spin around the planet, in this case, the Earth. And keep in mind that that is also an acceleration, even though if we are, let's say, standing on the moon and we are measuring the speed at which the moon is traveling around the Earth, it would seem a constant speed, but because it's not a straight line, because it's an angle, because it's curving, then it is actually an acceleration. It's the result of two vectors. Just like with our own, we can talk about our speed around the Earth, around the sun, I'm sorry, the speed of the Earth around the sun, you would say that it in itself is a constant speed, right? Because we're standing on the Earth, on the object that is moving. And we can say basically it's whatever hundreds of thousands of miles around the sun per year, right? In 1 year. In 1 year's time, we come back to the same spot where we were a year ago. However, it is not linear. It is circular, and therefore, to maintain that circular motion, it is actually an acceleration, okay, within the planetary system as a whole. All right, let me move forward from that. Again, to review, the accretion model talks about matter that is hot, typically white hot, right? And as it exerts gravity because it's matter, so it's attracting other matter that is floating around and flying, literally flying around, not floating, but flying around at incredible speeds, and it is impacting this larger matter that is like a proto-planet that will become a planet when it starts cooling down and stabilizing a little bit more. So it goes originally from white hot to red hot, all right? And as it does, it continues to attract matter, but then eventually it begins to run out of matter that is in the near vicinity. And the gravitational pull only extends so far, and it dissipates with space, with distance from the core, from the center of the planet. So eventually it will cool down enough to really have a crust, a solid crust, where liquid water can exist. And that for our planetary system as a whole has taken about 4.5 billion years. Just to review, keep in mind that a billion, this is an American billion, is 1,000 million, all right? It's 1,000 million, so this is 4,500 million years ago, is the formation of essentially the planetary system. Okay, now, yes, liquid water, keep in mind the range, which is from 0 to 100 centigrade, which is really a very narrow range when we consider the thousands of degrees of temperature above of the sun on one hand, and the thousands of degrees of temperature below zero for the blank of the universe, for the rest of the universe, okay? And we're just sitting at that exact distance where we have this little margin of temperature between 0 and 100 in the centigrade scale that allows for water to be liquid, and therefore allow for metabolism, for chemical reactions to happen in an orderly fashion within the liquid, and that's what we call metabolism. All right, back to the Earth, this being the geosphere, we have essentially three main layers, two of which are subdivided into inner and outer. So we have a core that is solid, and it is white hot, thousands of degrees. We'll see temperatures in a minute, but we have a core that is solid, and there's an inner core and an outer core. And then we have the mantle, which is also going to be an inner and an outer mantle, which is liquid, but a thick liquid, molten, we say, molten mantle. And then we have like lava, for example. And then we have the crust itself, which is solid crust, very thin, solid crust of just a few kilometers thick, where it's mostly covered by water, but then some continents stick out of the water to actually have dry land, all right? Dry land in quotations. Okay, moving forward, more. These are the cores that I talked about, inner and outer core. Then there's a lower and upper mantle and the crust. We're also going to talk about continental drift in a minute, which is moved by convection currents off the mantle itself. The theory of plate tectonics, which has been verified by various different facts, observations, and seafloor spreading, all right? Seafloor spreading. In other words, that the continents are actually rafts that are floating on top of the mantle and are very, very slowly moving away and toward each other on the surface of the Earth, on the crust. Okay, one more look at the layers of Earth from the core out, the inner and outer core, the inner core being solid, the outer core being liquid. Both are, like I said, quite hot. They are in the thousands of degrees of temperature, all right? And it's mostly iron, by the way, which is the most abundant element on Earth, is iron, and some nickel also. So it's a nickel iron core, and that is what is exerting the gravity. The gravity that we experience on the surface of the Earth, that 9.8 meters per second squared that Newton discovered, right, is the pull of gravity on the surface of the Earth. That is being exerted mostly by the core, which is this iron nickel ball, solid ball that is quite hot, all right, in the thousands of degrees still. And that's why we are little by little dissipating heat out through the various layers out into the atmosphere, and beyond the atmosphere into the universe. We lose heat. All right. Then moving into the mantle, the lower and upper mantle, which, as I mentioned, is molten, so it's liquid, but thick liquid, and is what we call lava, which periodically breaks through the crust in what we call volcanoes and volcanic activity. There are volcanoes that are on the surface of the Earth, and there are volcanoes that are underwater in the ocean. It's just fascinating. You can look at some of those films when a volcano erupts out underneath the ocean and is pouring out red hot molten lava, and it encounters the water, which typically is cold at the bottom of the ocean, about 4 degrees centigrade more or less. And the impact and the gases that form there, and the violent reactions that form when this molten lava comes out to the ocean, all right? So really, volcanic explosions on the surface of the Earth are much more mild by comparison to what happens under the ocean when a volcano, a volcanic ridge erupts. All right. And then finally, the crust itself, which is very, very thin, just about 100 kilometers, very, very thin compared to the thousands of kilometers that we have to the core, about 6,000 kilometers to the core of the Earth, all right? How do we know all this? How do we know these layers and can actually put a thickness to them in kilometers? All right, well, it's mostly from plate tectonics, the earthquakes, all right? So what happens is with an earthquake, there will be a wave that will propagate not only through the surface of the crust, causing the damage and the destruction that earthquakes cause within seconds, but also that wave propagates inside through the mantle because it's a liquid, all right? And even solid will propagate the wave, but there will be reflection and refraction occurring at different depths of the wave, of the propagation of the wave. So there will be a reflection bent out toward the surface again, all right? And even bounce on the surface and make a second reflection, or a refraction as it bends, as it enters one layer, for example, it passes from the mantle to the core and it will refract, all right? It will bend into, because it's a different density. Just like, for example, light coming from the atmosphere into water, it will bend, or if the water, and then if you have glass inside the water, it will bend again, all right, because different densities. And then when that wave continues to propagate, if the earthquake is strong enough, and it will come out on the other end of that core, it will diffract again into the mantle until eventually it will hit the surface of the Earth or the crust of the Earth somewhere on the other side of the Earth. And depending on how intense that earthquake was, it may be measured, all right, with instruments that are out there and how many minutes it took to get all the way out across. And because we know essentially from volcanic activity and lava, the density of lava, we can estimate the refraction, the reflection, and the refraction index to estimate then the thickness of that mantle. And then what is left, according to the periphery, the circumference of the Earth, what is left then has to be the core and so forth. So these estimations are done, and here's an actual graph of detecting. Here's the origin of the earthquake, the different waves, the different waves as they are detected, all the way out to half an hour, 30 minutes out from the epicenter of the earthquake, all right? and then they will have, one scale is the time of the propagation of the wave, the time lapse, and the other one is the latitude. From 0 degrees, for example, at the epicenter, latitude measured in degrees along the surface, the periphery of the sphere, all right? So with these two numbers, time and latitude, the reflection or the refraction index can be estimated to calculate the thickness of these layers and the composition of the layers also. So there it is, combination between earthquakes and tremors and volcanoes, volcanic activity. The inside of the Earth has been figured out by these geologists, all right? By proportion then, we have the core, which is mostly iron, then the mantle, which is about 70%. So the other 29%, more or less, is the core, and then the 70% the mantle, and 1% or less is the crust, that thin layer of only about 100 kilometers that has cooled enough in 4.5 billion years, again, to maintain liquid water. Okay. Now, I want to talk about convection currents because this is what I'm transitioning now into plate tectonics and the theory of continental drift. Literally what the word is saying, continental drift, that the continents, you think of North America, South America, Asia, Europe, Australia, and the subcontinent of India, and Antarctica, which is also a continent. These plates are sitting, these continents are sitting on top of the mantle, and they are like rafts that are floating around and are moving very, very slowly, but really moving. So it's in a large scale of thousands of years and millions of years. It's a dynamic system, okay? But very, very slowly at our scale of days and years and decades and so forth. And what is making all that, the continents floating and moving around, is the vertical movement of the mantle from the core to the crust, all right, in either a clockwise fashion, or counterclockwise on the opposite cell. And this movement of the mantle, because it is liquid, thick but liquid, right, molten, it is called a convection current, So I'm sure you've seen these things before, but just to review, here's a little video of a convection current. The background music makes it a little spooky, but just try to ignore the background music. All right, and let me turn on the volume and move it back. Beginning, okay. There's a little bit of showing convection currents.
Today, we're one of the most hypnotic things you'll ever see in a science class.
Raise the volume a little bit.
Have you heard that heat rises? Well, here you can see it's true for yourself.
That's the main thing, that heat
I've got
rises.
some food coloring on the bottom of a plastic container, and there's a hot mug right underneath the red food coloring. As it's heated, the water rises. But I want you to look closely and notice something else. The blue on the sides is being drawn in. You can see it better when I speed it up. Here's the thing I want you to remember. When water moves from one place, it doesn't leave a void behind. Water from somewhere else has to move in to take its place. That's why you can see the blue food coloring coming in from the sides. You can see it better from above. Watch that blue food coloring get drawn in. You can see it.
And then when it reaches the surface of the water, it moves down as it cools.
The hot water reaches the top, and then it gets pushed toward the edges by more hot water rising from underneath it. As it goes out to the edges, it starts to get cool, and cool water sinks just as hot water rises. And if you watch really carefully, you can see it sink and get drawn. back toward the middle. These are called convection currents, and you see them moving here in two big poles. They're one of the major things that drive ocean currents, especially in deep oceans. But it's not hot water rising that drives the ocean currents. It's really cold water sinking up near the poles. Here's a piece of ice that I froze with some blue food coloring in it, so you can see how cold water sinks. As water sinks at the North Pole, for example, water has to flow up from southern regions to take its place. And these currents travel around the globe, some of them taking 1,000 years to complete their course. Understanding convection currents will help you get a grip on weather systems and the movement of Earth's continents over the eons, and even the workings of a lava lamp. If you want to try this for yourself, click on this link for all the directions you'll need. Thanks for watching.
Okay, so even though this is in the context of water, so he's talking about this to make an example of the currents of the ocean currents, all right? But I'm using the concept of a convection current as such, this vertical rotation clockwise on one side and counterclockwise on the other side of the current itself to illustrate what is happening to the mantle as such. All right, so you can think of the mantle as a liquid that is thick but dynamic. And in contrast to the ocean currents that are being fueled mostly by cold on the poles, right? He mentioned it's cold water sinking and displacing bottom water up toward the surface and making that rotation movement, that vertical rotation movement. In contrast to that, the source of energy here is actually the heat from the core. You follow? It is the heat from the core that is heating up the mantle that is closest to the core, right? The lower mantle that is in contact with the outer core, and that mantle gets heated up, and so it rises because heat rises. And it's going to rise toward the surface until it hits up against the crust of the Earth, the bottom part of the crust, down an average of 100 kilometers, all right? It hits the bottom of the raft, if you will, of the continents, and it has nowhere else to go unless there is a crack. If there's a crack on the continent, what's going to happen? A volcanic eruption. A volcanic eruption, if there's a fissure, then a volcanic eruption will happen and lava will come out. But most of that lava stays underneath the crust and can only move then laterally. And as it moves laterally, it drags the continents to either side. Follow? Because it is thick. It is molten, thick, and so it's dragging the continents. In this example, this could be the mid-Atlantic, and it's pushing. This could be Europe on this side, and this could be North America on the other side, and it's pushing the two continents away, the two plates, right? And that is what is called plate tectonics. And then at some point, it will, as it's pushing the plates, it's also, it being the lava, the magma, the mantle, it is also, some of the heat is dissipated through the crust. Dissipates through the crust and through the oceans and out eventually through the atmosphere into space. And so it gradually cools a little bit. And so as it cools, it will sink and begin the cycle again. At the end of the day, when we look at the big picture of this, what is this doing? It is doing this convection currents of the mantle very slowly, but surely it is transferring heat from the core out through the mantle, through the oceans, through the atmosphere, out into space. So we're losing heat little by little, and we have been doing that for billions of years. Enough heat at some point was lost so that the crust can actually solidify, right? And form the plates, the continental plates. All right, let's look at a diagram from above. You can see the actual plates here. And all these are, the red are all seismic areas. They're the boundaries of the plates, and they're all seismic activity, all right? So, or seismic activity, volcano ranges, mountain ranges. And one that is very, very famous, for example, is this whole red one that goes around the Pacific. It's called the Pacific Rim. It's called the Ring of Fire. The Ring of Fire, because all of this is active volcanic activity, right? Including the San Andreas Fault over here in California. Or is California somewhere over here? That is, it goes a little bit into the continent, but mostly it's on the coastline and coming down Asia, the Philippines area, and here's the Korean Peninsula, for example, and then Southeast Asia and so forth, the Polynesian Islands. That is known as the Ring of Fire, very, very active volcanic activity. All right, moving forward a little bit. What this is then, it has moved the continents around over the millions of years, has moved the continents around. Once we had continents, in other words, once the mantle at the surface of the earth cooled enough to form these crust, right? The crust, solid crust, cool enough again to hold liquid water. There used to be one big supercontinent, all kind of stuck together, and that was called Pangaea. And Pangaea or Pangaea, it comes from the Greek, pan meaning all or every, like the Pantheon is the place of all the gods, right? Pantheos, it's a building with all the gods back in Rome from all the different conquests. And Gaia or Gaia is a reference to Earth. That's where we get Geo, for example. It comes from Gaia or Gaia, which is a Greek term for Earth, for Geos. All right, so Pangaea was this supercontinent that got fragmented, and it goes back only 250 million years ago, not even 1 billion of the 4.5 billion, you know, just 250 million, 225 million years ago, the supercontinent that fragmented, right, fractured, and started shifting and drifting from each other. The first big split was between north and south, more or less around the equator, between north and south, forming the top crust known as Laurasia, which includes mostly North America and Asia and Europe. So Laurasia is 3 big continents all clustered together, North America, Europe, and Asia, whereas the southern cluster called Gondwana, or sometimes you see the reference of Gondwana land included what is today South America, Africa, the Indian subcontinent, Antarctica, and Australia, all right? The cluster down here, that eventually also cracked up into further, what we know as the continents today, splitting the northern Laurasia splitting more or less into 2, North America on the west side, Europe and Eurasia. Sometimes you see this plate referred to as Eurasia, it's a single plate on the east. Whereas in the south, South America, which you can see fits nicely into the west coast of Africa here. India, which came out from the south, essentially a fragment between Antarctica and Africa, and India migrated, this Indian plate migrated drastically north until it crashed into Southeast Asia and continued to push up to generate the Himalayas, right? To wrinkle the Himalayas, the largest mountain range on Earth. And then Australia broke off from Antarctica to form its own mini continent. And so what the Earth looks like today, as you can see, a gradual separation from the original Pangaea just 250 million years ago. So this goes, the images here go counterclockwise, all right? What's interesting is that even at this stage, we already had life on Earth. Life on Earth all the way up to even the mammals, even though they were small, but real, And so when this continental drift happens, the various continents will take various representatives of species, of animals and plants, of course, and then through geographical isolation, evolution will continue to exert natural selection pressure, and we get speciation. But ancestors, their common ancestors, for example, the one that is very, very classic is the llama, the picuña, and the alpaca, and all these that occur in South America. They are all camelids. They're camelids. They are related to the camel and the dromedary, who are from Africa and from Asia. All right, and yet none of those camels and dromedaries, their ancestors, did not swim across the South Atlantic. Okay, rather the common ancestor of the camelids was already living in Pangaea, and one herd or several herds got over on this side, so a population, another population stayed on the western side, and when the split happened, then eventually speciation occurred through geographic isolation, which is a very common type of speciation. All right, back to the plates. Here they are by name, as you can see, and their motions relative to each other, which way they're moving, right? North, south, east, or west. You can see this is the relative motion of all these different plates in relation to each other. So the plates that are moving away from each other, for example, in North America is moving away from Eurasia. All right, then there is a mid-Atlantic ridge that is called a ridge, where there is coming up of magma and a huge mountain range in the middle of the Atlantic Ocean. It actually travels not only the North Atlantic, but also the South Atlantic, because the South America plate is also going away from the African plate here along the Atlantic. So it's kind of a zipper, moves throughout the center of the entire Atlantic Ocean. In contrast with the Pacific plate that is going into, well, there's actually what's interesting here is that the Pacific plate is moving that way, but the North American plate is moving faster than the Pacific plate. So there's a crunch on this side, and there is a buckling up of the two plates on the Pacific coast, which in the Northern Hemisphere, in the North American plate, forms the Rocky Mountains, the Rocky Mountain range, which then becomes the Sierra Madre Occidental in Mexico, in Mesoamerica, and then continues in the South American plate with the Nazca plate. Here is very drastic. We can see that the Nazca plate is actually pushing against South American plate, and that is causing the Andes, all right? So we have these two huge mountain ranges, the Rocky Mountains in North America and the Andes Mountains that are being formed by buckling up of two plates pushing up against each other. And certainly that is a more or less active volcanic region, at least for earthquakes. Okay, so here is a representation of the crust of the Earth without the water. This is from the National Geographic, and this is what is known as the geographic map, all right? We're showing the contour not only of the surface of the land, but also the surface of the ocean. Here is that mid-Atlantic ridge that I was talking about, which is a huge mountain range. The Himalayas, which are here, for example, pale. This is the largest mountain range on Earth, literally on top of the land, right? The dry land, the Himalaya range, but it is just like a little tiny hill compared to this mid-Atlantic ridge that goes all the way from the North Pole to the South Pole, humongous. And then this one here on the South Pacific, also another ridge where the plates are, where the magma is coming up and diverging and pushing away from each other. So here is pushing out, and here is pulling in, all right? Okay, enough of that. It's 11:15, so here would be, let me see for a moment. Okay. We can go back to the surface of the Earth. This could be a good moment to break. We're going to go into the biomes now and so forth. If you want to take a break now. Okay, it's 10, almost 11:15. So I want to take a 10-minute break here, more or less, and come back by 11. And we'll continue the second half as we start looking at life on the surface of the Earth, whether it's on the surface of the continents itself, dry land, or the water, the oceans, and also the fresh water that is on the continents. Okay, so let's take a little break here. I'm going to pause the recording, be back by 11 a.m. Okay, welcome back. We're going into the second half here, looking at now life on Earth, and not just the land part, but also in the oceans. We'll get to that a little later, but I want to mention that these large areas, mostly of vegetation, and then the animals and the fungi and bacteria that live in that area. These large regions, large geographical regions are called biomes, okay? And they are the largest category before we go globally into the biosphere as such. And there are these 9 basic biomes throughout the Earth, 9 biomes, beginning around the equator. The green is known as a tropical forest, or sometimes tropical rainforest, you see, and then moving north and south from there. But I want to point out that most of the landmass on Earth is in the northern hemisphere. Okay, so that's one characteristic, that currently, the way the plates are distributed currently, right, most of the landmass is in the northern hemisphere. Let's see, the equator is actually, it's not in the middle of this map. The equator is around here somewhere. Maybe this is the equator. All right, so it's not in the center of the map. And therefore, most of the land masses are in the northern hemisphere. It can be seen here better. So there is some, let's say, points of landmass that project into the southern hemisphere, mostly South America, the lower part of Africa, and then a little bit of Southeast Asia, and then Australia. And of course, the Antarctic, which is down here as a continent also. Anyway, moving out from the equator, whether north or south, we get a region of grasslands, which is known as the savanna, which is on the warm side. You can see there's a lot of savanna also in Africa and South America. Then there is a desertic region, which is mostly the Sahara over here and the Arabian Peninsula. And the center also, I want you to note, the center of Australia is one huge desert also, okay? And then some deserts in Asia and a little bit in North America. The polar regions, which would be not only the ice of the Arctic, but also the Arctic region includes a lot of Greenland and northern parts of Canada, and also some of Scandinavia up here, Iceland, all right? But also the southern, the Antarctica, the southern pole, which is a continent itself. But we can also have the same effect, the same cold effect, if we go up a mountain. We'll cover that in the next slide. It's called vertical stratification or vertical zonation, whereas this one is horizontal because this is on the surface of the Earth, whereas going up mountain, it is an elevation, and we get the same effect generally by way of change in vegetation going up a mountain as if we were to go away from the equator toward the northern or southern hemisphere. Chaparral is a unique vegetation that occurs around the Mediterranean. Mostly around the Mediterranean, it's chaparral. It's small trees and bushes and herbs, weeds that occur around the Mediterranean region. It's kind of unique. It's on the dry side, and it's called chaparral. Then the temperate grasslands, around 30 degrees north and south. You can see basically the center of North America, what is also known as the breadbasket, where a lot of agriculture is being done. And then 30 degrees south on South America, mostly Argentina, actually, maybe some Uruguay also here. But the middle of Asia, all right, a lot of this falls into China. And then also a strip around between the desert of Australia and the coastline. That's temperate, 30 degrees north and south generally. If it's not grassland, then there are going to be trees. So it will be a deciduous forest. A deciduous forest, as you can see, mostly the eastern half of North America, and then northern Europe, but not too far north, because then we get into a coniferous forest, and also East Asia over here. This is a woodland, and it's temperate because it's around 30 degrees parallel north. It means that they have more or less the 4 seasons, about 3 months each of the 4 seasons. You can think of the Carolinas, for example. We have about 3 months of spring, summer, fall, and winter. And so the leaves, the trees change their leaves, they drop their leaves, right? And that is called temperate or deciduous. The deciduous is a reference to shedding the leaves, this temperate forest. In contrast with the coniferous forest, which is mostly on the northern hemisphere, around 60 degrees, not 30, but 60 degrees north, again, because most of the landmass is in the northern hemisphere. The only equivalent in the southern hemisphere is along the Andes, the range, mountain range of the Andes, because of the vertical zonation, okay? And a little bit around Lake Victoria here in Africa. But the coniferous forest is, by definition, pine cones, so they are evergreens, pine trees. They're not deciduous trees, so they don't shed their needles. They keep the needles. In fact, they're actually shedding needles individually all the time, but basically they stay green as a whole throughout the whole winter, all right? And that is the blue up here, the light blue, the huge coniferous forest, also known as taiga. And then finally the tundra, which is the northernmost part of the vegetation. And tundra is, as you can see, only in the northern hemisphere. The reason for that is because the ground is frozen solid underneath. The thin layer of topsoil is frozen, so it's known as permafrost. And because of that, large root systems cannot penetrate that because it's ice. And therefore, you don't have trees up there. You only have bushes and herbs and shrubs that grow on the topmost layer of the soil, right? And that is the tundra. You can also get that tundra effect a little bit when you climb a mountain very high, especially in the alpine regions of, well, the Alps will be over here in Europe. It's very small, so it's not really shown on the map. It will be a little purple here and some of the mountains also in the Alps, in the Andes. Okay, so this is known as horizontal zonation because it's moving on the surface of the Earth horizontally from the equator, either north or south, all the way out to the poles, all right? And I mentioned that we can get a similar effect by going up a mountain in the tropics or the temperate region. So for example here, because this is a tropical rainforest, this would be at or near the equator. And the classical example of this is, again, the Andes mountain range, which goes clear across, well, here, this is the Andes range from essentially Central America all the way down to Tierra del Fuego, the southern tip of Chile. Mm-hmm. And along the equator side, which is around here, you get this effect. As you go up the mountain, the air becomes colder and colder and colder. So we get the same effect where we transition from a tropical rainforest to a temperate deciduous forest to a coniferous forest, right? Evergreen. And eventually we run out of trees, we run out of forest, and we go into a tundra-like region where you only have grasses and herbs and shrubs growing here because it's too cold and the water underneath is actually frozen. And so large roots cannot penetrate. And eventually, if the mountain is high enough, right, 10,000 feet or higher, what happens is then you get into an alpine region where you have basically ice and snow, very similar to the poles, to the North Pole and the South Pole, all right, equivalent, even though this geographically is occurring at or near the equator. It's called vertical zonation. Mm-hmm. Okay, that's as far as vegetation. Then of course, we will have entire ecosystems living in here. So when we place the animals and the fungi and the bacteria, then we complete the entire ecosystem, which is what a biome would be. And not just the vegetation, but also the animals and the fungi and the bacteria that would belong in that region. So we can come up with these two kinds of map. For example, this is a geophysical world where it shows just the natural environment, the natural surface of land or water. We can show also the geopolitical world superimposed, which is the human footprint, basically the continent, the countries, the nations of the world, close to 200 nations to this day, on top of the landmass. Just make this bigger for the sake of visualization. As you can see, each continent is subdivided into nations or countries, right? And so we have about 200 countries in the world right now. Australia being the only continent, I believe, that has a single country. And Antarctica that is only inhabited seasonally by scientists, but no permanent population that I know of in that other continent of Antarctica. And I think it's split up into various countries simply by convention of where they're doing research. All other continents are subdivided into political, geopolitical regions, countries or nations, okay? Little item of curiosity, I learned long ago that it only takes 4 colors. You only need 4 colors to be able to differentiate between the different countries of the world on a map. So that means that no more than 4 countries touch at any one point. And so you only need 4 colors to distinguish all the continents, all the countries of the world. All right, let's move forward. Getting more into the nature, the living systems, right, on Earth. This is just a brief introduction to ecology, which is the study of living organisms in place, in their geographical place, whether it's land or water. That is ecology. So it's on the opposite end of molecular biology. Generally, biology is divided into 3 main areas. From the cell in, including the cell, and inward is called CMB, cellular, molecular, and biochemistry, right? and it's all macroscopic. So we need obviously instruments, microscopes to look into that, that realm. Then we have organismal biology, which is essentially the organ systems and the organisms with, in and of themselves, individuals within any species, all of the organ systems that form that individual, but that's already macroscopic at the normal size of each individual organisms. Again, the 2 million species that have been discovered so far that we can actually see with our plain sight. And then the larger picture going from population forward, and that's what we're going to cover today toward the end of the lecture, moving from a cluster of individuals and forward. It's called population biology, and the field that studies that, that's ecology, because ecology includes also the relationship with the non-living systems. In other words, the atmosphere, the climate, the weather, the water quality, soil components, etc. Right? So we have biotic and abiotic factors make up the whole science of ecology. And that is the bigger picture of nature on Earth, because we know species lives isolated in a vacuum. They are surrounded by other species, by other organisms, and they also live, we all live within the context of a physical reality, what we call the abiotic, the non-biotic factors, all right? Okay, so it is this complex web of interactions, is very dynamic, of all the relationships of the organisms on Earth. Some key concepts here then that we're going to be looking at briefly is the food chain and the food web and the food pyramid. How food, what is known as the trophic level. Trophic level, you'll run across that word in a minute, because it is the food essentially that is keeping the organisms alive, right? And then we're also going to go look at these categories of population, community, ecosystem, biome, and biosphere. These are technical words that have specific meaning in science. So we're going to look at all these. Let's go forward then, keeping again the definition of ecology as a complex web of relationships between organisms in nature. Let's look at the trophic relationships, which is feeding relationships. You know that animals and plants and even fungi and bacteria are food for each other, right? So one organism is eating another organism, and that other organism is eating another one, and so forth down the chain. More or less it has to do with size, but it also has to do with producers and consumers, so that some organisms produce food and other organisms consume food, the food that is being produced. And that would be starting with a simple food chain, which becomes, when we see various food chains interacting with each other, that becomes a more complex food web. And then when we look at the actual biomass that is being passed on from one trophic level to the next, then that becomes a food pyramid. So let's look at some of these examples, going from the simple to the more complex, beginning with a food chain, just a simple food chain of 3 organisms. There is a producer and there are 2 consumers. One consumer is a herbivore, the other consumer is a carnivore. The words are meaningful. The producer, which typically are plants, they will produce food, specifically carbohydrates, and more specifically glucose, which can then get stored into starch, which are carbohydrates, they high energy molecules. And they do this through the process of photosynthesis. In other words, plants are able to take up light energy and transform it into chemical energy, store it in chemical bonds, specifically the covalent bond of carbohydrates, which is a high energy bond. And then what consumers do is they feed on that plant, and through metabolism, through the process of cellular respiration, which you know is the converse of photosynthesis, right? We break down those carbohydrates and obtain energy from that to do work. The kinetic work that is done is recharging the energy molecules of our own cells, which is the ATPs, the adenosine triphosphase, and that in itself allows for metabolism, for work to occur within the body, what we call metabolism. Okay, so remember at the biochemical level, photosynthesis is going one way and cellular respiration is the same reaction but going in the opposite direction. And the transformation of energy here is from light energy to chemical energy to kinetic energy of the actual work in the process of metabolism. As a result of that metabolism, we put out heat, which again dissipates out into space because it's energy that is unavailable for work and becomes part of what we know as entropy or disorder in the universe, because that heat dissipates and is not available for doing work. Okay, so the first level of consumers is always a herbivore, which means that they feed on herbs, on grasses, on plant material, right? They feed on producers. And then the next level in a simple food chain will be a carnivore, meaning the one that eats the herbivore. But this is also a second level of consumer because the carnivore is eating another consumer, okay? It's just a passage here from wheat to a mouse, to a field mouse, to a barn owl feeding on the mouse. This is a rather simplistic scheme. In nature, it's much more complex than that. So we go from simple chains to actual food webs, as you can see here, where each one of these lines represents a chain, again, beginning with plants and also some fungi could be here, saprophytes, because they're also, they can get eaten by primary consumers. But the layer of primary consumers typically involve herbivores of some sort. And in the plants, we also have to include algae, especially in aquatic environments or marine environments, where we have algae, which are a class unto themselves, but because they can photosynthesize, then they are producers, okay? We get the first layer of animals, which are herbivores. They can be rodents or birds, amphibians, insects, etc., or even as large as a mammal herbivores. Even reptiles, you may look around, and iguanas, for example, eat plants, eat flowers, and so they're kind of opportunistic, anything that is on their way, in their way. But they can also function as herbivores. Then we get an intermediate layer of animals that are called omnivores. Omnivores can eat either plants or animals. Precisely, the many reptiles are there, and some mammals and birds are omnivores, meaning that they can eat either plants or other smaller animals, okay? And then finally, on the very top, you get the top carnivores, which typically are larger mammals, and typically they're hunters, like the wolves, the coyote, all the felines are there, including our own mascot here at St. Thomas University, the bobcat. There used to be bobcat in South Florida. There's still a few around, but not too near a human population, okay? But those are known as tertiary consumers. They're the top layer of the carnivores. They're fewer in number, typically larger in size, and they are hunters. Then on the side here, I have also written in saprophytes. Saprophytes is very important because saprophytes are decomposers, all right? And saprophytes are of two kinds. Some are macroscopic and some are microscopic, but the decomposers are essential for maintaining the food web alive and going on. They are mostly fungi and bacteria. So fungi and bacteria, the fungi being some macroscopic that we can see, mushrooms, and others are underneath the ground mostly and are microscopic. And the hyphae are the filaments of these fungi, and the bacteria, of course, microscopic, okay? But if it were not for these saprophytes, we would just be covered with layers and layers and layers of dead organisms by now. We would just be buried in carcasses of dead organisms, plants and animals, all right? Entire forests, because no organism lives on Earth eternally. They all die. For example, our slash pine here, their lifespan is about 200 years. That means that on average, every 200 years, you know, these trees will die and new trees will come up to replace them and so forth, but the individual trees will certainly die and fall to the ground and then be decomposed, partly by the weather, by decaying because of weathering, right? Water and so forth, but also because of the action of fungi and bacteria, which accelerate the decomposition process. Thanks be to God. And so they're called saprophytes, which again comes from Greek and Latin. Sappho is death, is a reference to day or death or decay. And phyte is that they love dead decaying things. They feed on decaying organisms. That completes the food web as such. Now, we can also look at it quantitatively. This is kind of qualitatively, right? Looking at the different species that interact in the web, and it's pretty complex, as you can see. We can look at it quantitatively, and that's called the food pyramid. Food pyramid. And so here is an example of a food pyramid, several examples, beginning always with the bottom layer, which are going to be herbivores, whether it's on land, plants on land, or plankton, phytoplankton on the oceans, on water, all right? So we got plants on land, or we got phytoplankton in the oceans, in the water, and that's the first level, the first trophic level in a food pyramid. Then above that will be, so the herbivores, and also the phytoplankton, I'm sorry, the zooplankton, in other words, the animal component of plankton, which is still microscopic, and is feeding on the phytoplankton. That's going to be the next layer of organisms feeding on the herbivores. Above that will be the omnivores, the second layer. There could be a third layer and a fourth layer of carnivores, all right, or actually two layers of omnivores. The point here is that by biomass, in other words, by bulk of the matter, of the weight of the plant or the animal, every trophic level is diminishes by 90%, or it's a tenfold condensation, if you will. Another way of saying this, for zooplankton, all right, for zooplankton to put on 1 pound of weight, it needs to eat 10 pounds of phytoplankton, all right? Or for a herbivore, let's go to land, which is a little easier. For a strict herbivore, like for example, a mouse that only feeds on grains or grass, all right? For a mouse to put on 1 pound of weight, it needs to eat 10 pounds of grass or 10 pounds of wheat, all right? And then for a fox to put on 1 pound of weight, it needs to eat 10 pounds of mice. Or for a seal to put on 1 pound of weight, it needs to eat 10 pounds of fish, okay? For a fish to put on 1 pound of weight, it needs to eat 10 pounds of zooplankton. So on up the scale. When we get to the top carnivore, the top of the tippy top of the pyramid is typically a carnivore, all right? So for a polar bear to put on 1 pound of weight, it needs to eat 10 pounds of seal, all right? And so that's the trophic level of a tenfold increase down the pyramid or decrease up the pyramid, whichever way you're looking at it. And the same level happens more or less in a temperate region and in a tropical region. So for example, this is showing a polar region, right, on land or on water. We can make the same argument in the temperate region, remember, about 30 degrees north of south, where the climate has the 4 seasons more or less evenly. For a, what is this, a pheasant to put on 10 pounds, to put on 1 pound, it would have to eat 10 pounds of grain. The same for the rabbit, primary herbivore, to put on 1 pound of weight, it would have to eat 10 pounds of grass, okay? And then what's up here, a fox or coyote, whatever is feeding on the pheasant or the rabbit, for that fox to put on 1 pound, it will have to eat 10 pounds of rabbit. Same argument in the tropical region. The same in tropical region. For the giraffe to put on 1 pound, the giraffe is a herbivore, it needs to eat 10 pounds of grass. For the lion to put on 1 pound, it needs to eat 10 pounds of giraffe. Right? So these trophic levels apply more or less at this tenfold increase or decrease, whichever way we're going up or down the pyramid. And that is for biomass. Biomass, which is the actual bulk weight of the plant or the animal or the fungus. All right, moving forward then, finally, what we have to establish is this hierarchy of life going beyond the individual organism. Think species. Each species is made up of individuals, right? Of that same species. When 2 or more individuals of the same species come together, they form a population. So by definition, all of the individuals in a population belong to the same species, all right? And what is the biological definition of species? That they can interbreed, they can mate and produce fertile offspring. Remember Meyer for the biological definition of species, okay? So when 2 or more individuals of the same species, cannot emphasize it enough because this is where typically students get confused. Of the same species, 2 or more individuals come together, they form a population. And then you can have several populations of the same species that are geographically isolated. All right, when populations of the same species become geographically isolated, then natural selection can act selectively, more pressure in one region, less pressure in another region for perhaps abiotic factors, and then speciation may begin. All right, and eventually, if enough selector's pressure is placed on that region, that population may eventually diverge from another population of the same species, so that time later, years or decades or centuries or millennia later, those 2 populations of the species come back together, they will not be able to recognize each other, okay? And then we can say that speciation has begun. Evolution, yes, going on over relatively long periods of time by the separation of populations of the same species that eventually will diverge into other species. Okay, now when we have populations of different species, listen to me, population of different species coming together, interacting with one another, which is more realistic what happens in nature, right? Then those form communities. For example, in this complex food web, right? These for example, these herbivores here, the primary consumers, they may interact. You may have squirrels living together with deer, with elk, and also there may be some birds living together in that same forest and so forth, and there will be some frogs around and butterflies. Those different species, populations of these different species coming together, they form communities, right? I'll give you some examples in a minute so that you can see them. So communities are the living organisms or interacting with each other, eating or getting eaten by each other, escaping from each other, etc. When we add the abiotic factors, the non-biotic factors to those communities, in other words, the temperature, the pressure, the humidity, the soil composition, the amount of heat, etc. Then we have added the abiotic factors, the non-biotic factors, the weather systems, for example. Then we are talking about ecosystems, okay? So you see that the picture becomes more and more realistic when we have biotic and abiotic factors coming together. That is the ecosystem, and that is what ecology studies. Ecology studies ecosystems. When we have ecosystems coming together in large geographical regions, then those are biomes. The 9 biomes that I talked about earlier, those are several different ecosystems coming together in a large geographical region, whether it's on land or in the oceans. And those are the biomes. And then finally, when we put all of the different biomes together of the whole world, that's the biosphere. All right, all the living organisms on Earth, on the surface of the Earth, below the surface of the Earth, and in the oceans and the water systems as a whole, that is the biosphere, which is made up of these about 9 biomes that I was talking about earlier. Okay, let's look at some examples now. Here we have populations. We have several different populations here. We have, for example, a population of how many tigers in this pride. It's called a pride of the felines, right? Here we have a population of 4 tigers. There's mama tiger and 3 cubs, okay? So this is one population of tigers. All right. Then here is a population of emperor penguins in Antarctica. There, I haven't counted all these, but I would say that there are maybe 50 or 60 or maybe 100 penguins here. This is a population because they're all the same species. These are emperor penguins in Antarctica. You can tell it's Antarctica also because of the huge mountain range back here, all right? One of the penguins is facing the other way, but that's still an emperor penguin there, okay? Actually, when you look at this photograph a little closer, you will see this dark dots back here, these black dots. That's another population of penguins. And you can bet your bottom dollar, those are going to be also emperor penguins, which are the ones that are in Australia. All right, so this is another population of the same species of emperor penguins here on the horizon, way in the background. You see it? So we got 2 populations of emperor penguins, all right? And they're close enough that there's probably some interaction. Some of these individuals here might migrate over to this population, and this other, there'll be migration back and forth. Remember, that is drift. Remember, chance migration, drift from one population to another as far as the gene pool is concerned. So as long as that migration is occurring back and forth, then these 2 populations are pretty much the same, and they can most likely interbreed with each other. However, if now there will be a crack here in the ice and these 2 populations drift away from each other, hypothetically, let's just take Antarctica and split it into 2 subcontinents, right? And this one population of penguins ended up on the east side of Antarctica, and this other ended up on the west side of Antarctica. They start off as 2 populations of the same species of emperor penguins, but over time, there may be some genetic differences that occur, starting with chance mutations, and then the other factors that are selecting out the weaker and so forth. So there could be also a bottleneck effect of the gene pool, so that over a long period of time, maybe those 2 subcontinents of Antarctica come back together, and these 2 populations, A and B, meet again. And even though they may look identical to us, you know, a penguin from population A and a penguin from population B may look identical to us, but among themselves, they may be able to distinguish differences enough that they don't recognize each other as the same species, and they will not interbreed. It could be a smell, for example, that we wouldn't detect, okay? They both smell nasty to us, but to each other, one smells nicer than the other, and so they will not interbreed. And that could be the beginning of speciation, to eventually get a different species of penguin from what used to be 2 populations of the same species. All right, The same argument can be made with plants. And here we have a population of pine tree of some sort, a coniferous forest, and it's pretty homogeneous. This is called also the dominant tree. The dominant tree is typically the largest and most abundant tree in any forest. And it's typically 1 or 2 or 3 species, not too many species. And this, at this point, when we have dominant trees like this, unless the climate changes drastically or significantly, there is a replacement level and it becomes a climax community. It pretty much stabilizes with that 1, 2, or 3 species as the dominant species, okay? And that is called a climax community. With climate change, then the population can also change. Here, at the smallest scale, so this could be basically the largest scale at the level of an entire forest, in this case, a coniferous forest. At the other end of size of the smallest scale, these are actually bacteria. It's a photograph of bacteria. It's a micrograph, a microscopic photograph of cocci. Cocci, which are circular bacteria, little balls that form colonies. And you can see here's one population of cocci, here's another population of cocci, and here's a third population of cocci of these bacteria, right? One coccus, several cocci. So we can assume that these are closely related to each other because the actual distance is very, very tiny, but over time, these could become isolated and eventually evolve into a different type of bacterium. All right. But for now, these are 3 populations of the same species of bacteria. Moving forward, here's another example. Increasing the number of species, of different species, this would represent like a little community. Why is it a community? Well, we got turtles. We got a population of turtles. How many population? This is probably hawksbill turtle, some kind of a sea turtle, right? How many individuals in this population? 3 individuals, there they are. 3 individuals of this small population of sea turtles. But there's also these dark fish, they're called tangs. These are typically blue tangs, right? And there is 1, 2, and possibly 3 and 4 here. So it's a population of tang fish, which is 1 species of 4 individuals. And then there are also these other ones. These are also tangs, but it's a different type of tang. I forget the name of this tang, but there's 1, 2, 3, 4, 5 of these other guys, which forms another population of tangs also, but different species of tang. And then, not to mention the coral, which seems to be pretty bleached out. But if this coral were living, then we'd have many more individuals of different species here. This looked like used to be a brain coral of sorts. They look kind of bleached out right now. When they were still alive, this basically would be a community because it has populations of different species living together, interacting, okay? So this would be a community. Population of different species together. Then, making it more realistic still, here is just a caricature of a deciduous forest, right? It's not a tropical rainforest. It's not a coniferous forest. But maybe in the background here is a coniferous forest up in the mountains. But this one, the leaves, they're leaves, not needles, right? So these leaves will be shed in the fall season. They will fall off in autumn and then go into winter dormant. And we see that the animals also belong to a temperate region. Many mammals here, nice and woolly and hairy, the deer, the raccoon, the squirrel, the bear, the wolf, etc. There are also some birds, some fish, some reptiles. Here is an arthropod, a crab, etc. Some grasses and weeds. So these are all living organisms, but also this implies that there is water, there is liquid water, there is water vapor in the atmosphere, there is a particular temperature, humidity, amount of sunlight, soil composition, etc. So those are the non-living factors, the abiotic factors that make up the ecosystem. So this is an ecosystem, all right? It's a local ecosystem of living organisms interacting. And of course, we have to include in here that we don't see directly, but they're in there, the fungi, the mushrooms that are in there, and the bacteria, which this is obviously covered with bacteria that are microscopic and we can't see, but they're also part of the ecosystem, okay? Then we can look at when various ecosystems come together into a larger region, right? We go into the biomes, So these are large geographical areas composed of various ecosystems or more local ecosystems. And they are major terrestrial biomes, which can be the grassland, the desert, the forest, and the tundra. These are the four major terrestrial biomes. Temperate grassland or forest, which can be tropical, temperate, or coniferous forest. Desert, very dry, very hot in the day, very cold at night because it has little humidity and humidity holds on to heat. So as soon as the sun goes down, this becomes very cold. And that's why in movies of the Middle East and so forth, we see people bundle up with all these layers of clothing and we say, oh my goodness, it just makes me hot to watch them. Yes, they're hot in the day, but at night, they need all those layers of clothing, thick clothing, because it gets very cold in the desert at night. Very, very little humidity. And the tundra, again, keep in mind, permafrost. Therefore, underneath the ground is ice and trees cannot take root here. And so it's only small shrubs and grasses and herbs. We also have major ecosystems or biomes in water. We can look at freshwater or brackish water first. Brackish water is in between, like estuaries, where the rivers empty out into the ocean and there's mixture because of ocean currents and rise and fall of the river seasonally by more or less water flow, fresh water flowing, right? So that interaction of fresh and salt water is called brackish water. Those are known as estuaries. They're very rich in biota, by the way, in plants and animals. A lot of algae grow here. And when algae grows, then you have all the other, the zooplankton, and then the small animals that feed on that, the fish and other arthropods, crustaceans and so forth, and mollusks. And you get up the food web. They're very rich. Estuaries are very, very rich in animal and plant life. In fact, along the shoreline, the littoral region, well, I'll talk about that in a minute. Let me hold off from that thought. Rivers are also major biomes. Lakes or swamps or marsh are also considered biomes. They're fairly large areas, geographical areas, where you have biodiversity, right? Biodiversity. And we have the same on saltwater and the marine environment. Major marine environments. There are three major marine environments. The coast, the coastline, which is also known as the littoral or the shoreline, okay? Then there is the pelagic region, which is the open water column. Pelagic region, some fish live the bulk of their life in the pelagic region, basically swimming. In fact, most sharks need to be swimming because they need water to run through the gills. They lack muscles to push water through their mouths and through the gills. So most most sharks, especially open water sharks, need to be moving all the time. That's why it's so deadly for them. When they get trapped in fish nets, essentially they asphyxiate to death because they can no longer move through the water column and they run out of aerated water, right? Oxygenated water. All right, and then the benthic region is the bottom of the ocean. Now, the bottom of the ocean starts all the way from the littoral edge, if you will, into the ocean, all the way down into the abyss, all right, the deep ocean floor. And that whole surface of the bottom of the ocean, from very shallow to very deep, all that is called the benthic region. Benthos, the deep, or the floor, the ocean floor. Okay. So when we put these together, it turns out that we have the, here is called the ecosphere, which would be the geosphere, but what is alive on top of Earth, right? On the land is known as the ecosphere. Then lithosphere is a reference to rock. Lithos is a rock or stone or pebble. And then the hydrosphere is water. The atmosphere is the air. And putting all those together, that's the biosphere. Okay. So here is a photo of planet Earth. And this is an actual photograph, not a painting, but an actual photograph where you can see this blue little dot floating in the middle of space in the solar system. And the background is just dark, deep, dark space. And we have a very thin layer of atmosphere that is keeping us sheltered from impact of asteroids and meteorites and all that to maintain life. And then the water, which is mostly the liquid water that we see, but also the clouds, which is water vapor. And we see various hurricane systems actually developing here. There's one going through Western Mexico or Central America here. Here's the Caribbean, Peninsula, Florida. Okay. So far, the only planet we know of that has life for sure. There's a lot of speculation about the others, the other planets, and especially the exoplanets. But the key, at least at the organic level, that we would recognize it as life is this whole issue of liquid water, all right? Which again goes back to that range, that narrow range of 100 degrees in the centigrade scale. And due to the distance that we have essentially from Earth to the sun, plus also the heating that is occurring from the core, right, out through the crust that contributes to maintaining liquid water. We are also in an interglacial period. I would mention that because we still have natural ice, significant amount of natural ice on Earth, essentially the two poles, the North Pole and the South Pole. And because of that, then we are in an interglacial period between a tropical Earth, where it would be just totally covered with liquid water, and the sea level would be much higher, anywhere from 100 to 200 feet of salt water above us, or a total winterization, which would be 1 or 2 miles of ice on top of us with the glaciers, okay, the glacier, a full glacial period. And much less of the continents exposed, and the sea level lower, of course, because then that ice has to come from some kind of water, and it is water that has evaporated from the oceans and has become frozen, and through snow has deposited into glaciers. So that would be a full winterization of the Earth, and we are somewhere in between because we have ice, but the whole Earth is not covered with ice, and we have liquid water, but we're not totally full of liquid water. So we are in an interglacial period. It's anybody's guess which way we're going, if we're going to our tropicalization or winterization, but also the fact that our lifespan is relatively short when we consider geologic time, okay? Because our span, like the Bible says, 70 years or 80 for those who are strong. It's interesting that that is pretty accurate. It seems to be that the average lifespan of the human in good health is about 80 years of age, more or less, right? Which is very, very small compared to geologic time, which is typically measured in thousands of years or hundreds of thousands of years or even millions of years, right? To get to the 4.5 billion of the age of the whole Earth. That would be more relevant when we talk about climate change in contrast to weather and so forth. So the fact that it's warming, that this summer is the warmest summer ever, that we have been recording temperatures on Earth doesn't necessarily mean that we're moving to global warming. It just means that we have a warmer summer this summer. But if that continues to occur over hundreds or thousands or hundreds of thousands of years, then we can say that we're definitely heading toward tropicalization and global warming. All right? But it's the time scale that is so challenging, because thermometers have been around maybe, I don't know, you want to put it in centuries, it's still within the framework of weather and not climate. So that's the challenge. So we have to measure then the temperature of Earth on the surface indirectly, looking at ice deposition and the organic and inorganic matter that has deposited in the ice layers, the ice cores that have done through Arctic and Antarctica, to determine what kind of weather or climate was going on thousands of years ago. Okay, so that's it for the introduction to the geosphere, okay, which is our planet here on the inner planets. And then we're going to move next lecture into the hydrosphere, atmosphere next. We'll look at atmosphere next Saturday, and then hydrosphere, and so on, until we get to the human population and our footprint here on Earth, and what is being known as the Anthropocene, this new age that we are generating by way of the artificial things, the stuff that we're introducing into Earth, including the pollutants and the increase in CO2 and all that. All right. Questions, comments, anything? Okay, it's just coming up to noontime, so I'm going to stop here. If there's nothing, and turn this into the YouTube. Okay, if there are no questions, then I'm stopping the recording.